Good morning, students. Today we are going to discuss about gear trains. Now, what is a gear train actually? When two or more gears are meshed with each other to transmit the power from one shaft to the another, you call such combination as a gear train. So, these gear trains are going to reduce the speed and increase the torque of the output shaft. And these are also used to bridge the gap between the driver and the driven gears. And let us see and that's the definition. Let us see the different types of gear trains. The first one is a simple gear train, and we also have compound gear train, reverted gear train, and epicyclic gear train. Now, what is a simple gear train actually? When you have only one gear that is mounted on a shaft, you call such arrangement as a simple gear train. When there is more than one gear that is mounted on a shaft, you call such an arrangement is called as a compound gear train. The third one is a reverted gear train. When the axis of the input shaft is coaxial to the axis of the output shaft, you call such a combination as a reverted gear train. And the last one is epicyclic gear train. When one gear rotates upon and around the other gear, such a combination, you call it as a epicyclic gear train. The first one will start with the simple gear train. As I told you, a simple gear train means when only one gear is mounted on a shaft, you call such a combination as a simple gear train. Now students, now you can see the diagrammatic representation here. The gears has been represented as circles. You could ask me how you can represent a gear as a circles without showing their teeth. But you see the circle which I am representing here to show the simple gear train arrangement is a pitch circle, because pitch circle represents the design, that is the size and shape of the gear. Therefore, a pitch circle can be used directly to represent a gear. Now you see in the first diagram, two gears, that is gear 1 and gear 2. The first one is a driver gear and the second one is a driven gear, are meshed with each other directly and externally. And you see the driver gear is rotating in clockwise direction and the driven gear will automatically rotate in anti-clockwise direction because 1 and 2 are directly meshed with each other. Now in the second combination, you have a middle, that is an intermediate gear between the driver and the driven. Now this intermediate gear, we call it as idler gear. Now what is the purpose of this idler gear in a gear train? These idler gears are generally used to bridge the gap between the center distance between the driver and the driven gears, or it can also be used to change the direction of rotation of the driven gear. For example, if the driver gear, you see in this example, the driver gear is rotating in clockwise direction, and if you mesh the driver gear directly with the driven gear, as in the combination first, as we have seen in the first combination, the driven gear will rotate in anti-clockwise direction. But if you want the driven gear also to be rotated in the same direction of the driver gear, you have to add one more gear in between the driver and the driven, that is the intermediate gear. You could also call it as an idler gear. Now you see the gear 1 is meshed with gear 2, and now the gear 2, that is the intermediate or idler gear, is meshed with gear 3, that is the driven gear. Now if we rotate the driver gear in clockwise direction, this gear 1 is, because it is directly meshed with gear 2, now the intermediate gear or the idler gear 2 will rotate in anti-clockwise direction, and this, because this 2 is meshed with the output or the driven gear, now the driven gear will also rotate in the same direction of the driver. That is the use of, you call it as intermediate or the idler gear. Now in the simple gear train, you see, you can also see the animation of the simple gear train here. A simple gear train consists of, a driver, idler gear, and the driven gear. Generally, the driver gear will be mounted on the input shaft where the input rotation is given, and the driven gear is mounted on the output shaft where the output is being taken from the output shaft where the driven gear is mounted. Now we have three elements here in the simple gear train. As I told you, what is a simple gear train actually? A simple gear train means when you have only one gear mounted on a shaft, you call such a combination as a simple gear train. And you see we have three gears here. The first one is the driver gear. Driver gear will also be mounted on an input shaft. And the driven gear, the third one, the driven gear is mounted on the output shaft, and the third one is the idler gear. The purpose of idler gear is to change the direction of motion of the output shaft, or it can also be used to bridge the gap, and it can also be used to bridge the gap between the driver and the driven. Now you see, let us consider the speeds. Now you see this combination when the driver is directly measured with the driven. Let us consider N1 is the speed of gear 1 and N2 is the speed of gear 2, that is the driver and the driven, and T1 and T2 be the number of teeth on gears 1 and 2 respectively. And there are some basic definitions that have to be taught here. Actually, the first one is the gear ratio. Gear ratio is defined as the ratio of omega 1, the angular velocities of driver to the driven, that is omega 1 by omega 2 will be equals to n1 by n2, that will be equals to d2 by d1, that is equals to t2 by t1. You see here the relation between the speed of the gear and the number of teeth are inversely proportional. And the second important definition that you could see is the speed ratio. That is very important in the part of the numericals. The speed ratio is defined as the ratio of speed of driver to the driven, that is n1 by n2 is equals to t2 by t1, inversely proportional to the number of teeth. And the train value, the third one that is very important that you have to learn here, is the train value. What is the train value? It's inversely proportional to the speed ratio. That is, train value is defined as the ratio of speed of a driven gear to the driving gear, that is n2 by n1, which is equals to t1 by t2. So these three definitions are very important. The first one is gear ratio, second one is speed ratio, and the third one is the train value, which we are going to do some numericals by using these formulas in the forthcoming slides. And coming to the applications of the simple gear train, the simple gear train is also used in automobile gearboxes, and it is also used in heavy machinery, which duty process and lathe machines. Okay, and the next one that we are going to discuss about is the compound gear train. As I told you, what is a compound gear train? When you have more than one gear that is mounted on a shaft, you call such a combination as a compound gear train. Now, students, you can see this diagram, and these compound gear trains are also used to obtain the higher gear ratios. You see, this diagram represents 6 gears. You see, the first one is a driven gear. The second and third is a compound gear. Fourth and fifth is also another compound gear. The sixth one is the driven gear, which is mounted on the output shaft. And the driver gear will be, that is the gear 1 is mounted on the input shaft, that is shaft A. And shaft B, here you can see the shaft B is a compound gear train which has gears 2 and 3, and shaft C is also having a compound gear with gears 4 and 5, and shaft D is the output shaft where on which the gear number 6 is mounted. Now you see, when I rotate this, you see here the gear 1 is meshed with gear 2, and you see 2 and 3 will be on the same shaft, therefore the speed of 2 and speed of 3 will be same, and even the direction of rotation will also be same because 2 and 3 are compound gears. That means because 2 and 3 will be is mounted on the same shaft. And you see 3 is meshed with 4, and 4 and 5 will rotate in same direction because 4 and 5 together called as compound gears, and 5 is meshed with 6. Now you see this combination, The gear 1 is rotating in clockwise direction and is meshed with gear 2 externally. Therefore, gear 2 will rotate in anti-clockwise direction. And because 2 and 3 are compound gear trains, when gear 2 rotates in anti-clockwise direction, 3 will also rotate in anti-clockwise direction. And 3 is meshed with gear 4 externally. Because 3 is rotating in anti-clockwise direction, the gear 4 will rotate in clockwise direction. Because 4 is rotating in clockwise direction, 4 and 5 are compound gear trains, therefore automatically the gear 5, which is on the same shaft, will also rotate in clockwise direction. And because the 5 is measured externally with the driven gear, that is the output gear 6, which will rotate in anti-clockwise direction, because the fifth gear is rotating in clockwise direction. Therefore, this combination that has been shown here is when the input driver is, that is the driver shaft or the driver gear, driver shaft is rotating in clockwise direction, the driven will rotate in anti-clockwise direction here. That, I mean, that type of combination has been shown here. Now you see, you can also see this animation. You can see this. You have a compound gear, the first one, and you also have an idler gear in between. As I told you, what is the importance of idler gear? The idler gears are used to bridge the gap between two shafts, and they are also used to change the direction of motion of the output shaft also. And then you have compound gear here. You have this second compound gear is having 3 gears. See, when you have more number of gears, they will, we can increase this, the gear, that is, you can increase the torque to the output gear. You see, this is the output gear. Now, what are the elements that are in the compound gears? The first one is the input gear, which is mounted on the shaft, and the second one is the output gear, which is mounted on the output shaft. The third one is the compound gear, which is the main gear, which is used to, which will affect the gear ratio actually. And the fourth one, the very important one, is the idler gear. As I told you, the importance of the idler gear is used to reduce the uh, distance between, or it is used to reduce the distance between two shafts, and it also, it is also used to, what you call, it is also used to change the direction of motion of the output gears. You see, these are the advantages and disadvantages. What are the advantages of the compound gear train? Is, you have this compound gear trains are very advantageous in having higher gear ratios, and the efficiency and the transmission efficiency will be high without having any slip, and it is also having higher speed reduction ratio with less center distance. And what could be the disadvantages? Now, because when we mount more number of gears on a single shaft, the main disadvantage that could be caused is the high noise. Because of this high noise, and automatically we have to lubricate it more to reduce the friction between the teeth between the gears. Therefore, high lubrication is also one of the disadvantages. But where it actually used, what is the application of the compound gear train? These compound gear trains are used in wall clocks, and they are also used in drilling machines. They are also used in lathe machines. They are also used in, you see, timing gears in the vehicles. Timing gears means, in the internal combustion engines, where we timely open the inlet and the outlet valves. These are some of the applications of the compound gear train. Now, in this slide, you can see the same figure of the compound gear train, and we are going to calculate now the speed ratio of the compound gear train. Now you see here, when you calculate the speed ratio of the compound gear train, let us define what is a speed ratio. Speed ratio is defined as a ratio of speed of driven, sorry, the ratio of speed of driver to the driven gear. Now you see here, we have, in this example, we have 6 gears. That is, gear 1 is meshed with gear 2. 2 and 3 are compound gears. That means 2 and 3 will be on the same shaft. Therefore, the direction of rotation of 2 and 3 is same. And 3 is meshed with 4 externally. 4 and 5 are compound gears. And 5 is meshed with 6 externally. Now, for this combination, if you would like to calculate the speed ratio, as I told you, the definition of speed ratio is the ratio of driver to driven, the speed of the driver gear to the driven gear. Now, you see here in this combination, you see the driver gear, that is 1, is meshed with 2. Therefore, if you could calculate the speed ratio between 1 and 2, that is, the speed ratio is N1 by N2. Here it has been shown N1 by N2 is inversely proportional to the number of T, that is T2 by T1. Let it be equation 1. And because 2 and 3 are compound gears, therefore the speed of 2 and the speed of gear 2 and the speed of gear 3 is same. And now you see here, the gear 3 is meshed with gear 4. Therefore, you can calculate the speed ratio between 3 and 4. If you calculate the gear ratio between 3 and 4, now for the combination 3 and 4, 3 will be driver and 4 will be the driven gear. Now, when you calculate the speed ratio between 3 and 4, it is N3 by N4 is equals to T4 by T3. That will be your equation 2. And after calculating the speed ratio between 3 and 4, and because 4 and 5 are compound gears, so we won't calculate the gear ratio between 4 and 5 because 4 and 5 are compound gears. Therefore, the speed of 4 and speed of gear 5 is same. Now, when it comes to 5 and 6, the combination between 5 and 6, because 5 and 6 are measured with each other externally, and 5 and 6, the 5 will, for the combination 5 and 6, 5 will be driving gear and 6 will be driven gear. Now, the speed ratio between 5 and 6 will be N5 by N6 is equals to T6 by T5. Now, if you multiply all these three equations, the speed ratio equations between 1, 2, 3, 4 and 5, 6 gear, it will be equals to like this: N1 by N2 into N3 by N4 into N5 by N6 will be equals to T2 by T1 into T4 by T3 into T6 by T5. As I already told you, the gears 2 and 3 are compound gears, 4 and 5 are also compound gears. When you have a compound gears, the speed of those two gears are same. Therefore, that is speed of 2 and 3 is same and speed of 4 and 5 is same. Therefore, N3, N2 gets cancelled, N5, N4 gets cancelled. Therefore, for the whole combination of these 6 gears, the speed ratio, as I told you, what is the definition of the speed ratio? It is the ratio of the speed of driver gear to the driven gear. For the combination of the entire 6 gears, the driver gear is gear 1 and the driven gear is gear 6. Therefore, N1 by N6 will be equals to T2 into T4 into T6 divided by T1 into T3 into T5. As I told you, the number of teeth are inversely proportional to the speed. This is how the speed ratio can be calculated for the compound gear train. Next one that we are going to see is the reverted gear train. Now, what is a reverted gear train actually? As I told you during the starting of the lecture, when the axis of the first gear is coaxial to the axis of the last gear. First gear means here the driver gear, the last gear means here, here the driven gear. When the axis of the first gear is coaxial to the axis of the last gear, that is the driven gear, you call such type of combination as a reverted gear. Now you can see this reverted gear train in the figure. Now you see the first one, is a gear which is mounted on the input shaft or the driver shaft. Now the first gear is measured with gear 2. Now when gear 1 is rotating in clockwise direction, gear 2 will rotate in anti-clockwise direction. 2 and 3 are compound gears. Therefore, when gear 2 rotates in anti-clockwise direction, 3 will also rotate in anti-clockwise direction. And 3 and 4 is on the back side of 1. 3 and 4 are measured externally. When 3 rotates in anti-clockwise direction, 4 will rotate in clockwise direction. But you see, when it comes to the axis of the output shaft and the input shaft, that is gear 1 which is mounted on the input shaft and gear 4 which is mounted on the output shaft, the axes are coaxial. This type of combination is called as reverted gear train. Now what is the advantage of this reverted gear train? Means these reverted gear trains will occupy less space, and because the driving gear is coaxial to the driven gear. That is the main advantage, and it has less noise also. And these are also used in, see, this combination reverted gear trains are used in lathe machines, and these are also used in milling machines, drilling machines, etc. And now you see this, if you this combination, because we need to calculate the speed ratio. As I told you, speed ratio, what is the speed ratio? The definition of the speed ratio is the speed of driving gear to the driven gear. Because we have 4 gears here, 1, 2, 3, and 4. The driving gear is gear 1 and the driven gear is gear 4. N1 by N4 is equals to product of number of teeth on drivens divided by product of number of teeth on drivers. Driven gears are 2 and 4. Therefore, T2 into T4 divided by T1 into T3. Or you can also calculate in this way, because 1 is measured with 2. If you could calculate the speed ratio between 1 and 2, N1 by N2 is equals to T2 by T1. And 3 is measured with 4. If you could calculate the speed ratio between 3 and 4, N3 by N4 is equals to T4 by T3. So if you multiply that, N1 by N2 into N3 by N4 is equals to T2 by T1 into T4 by T3. Therefore, N2 and N3 will get cancelled because N2 and N3 are compound gear trains. Therefore, the total will be equals to N1 by N4 is equals to T2 into T4 divided by T1 into T3. And the other one, by assuming the module of all the gears to be same, from the figure you can see the combination. First you see the combination between gear 1 and gear 2. You see the distance between the center distance between gear 1 and gear 2. The center distance between gear 1 and gear 2 with combination with gear 3 and gear 4 can be written as, for gear 1 and gear 2, that is the radius of gear 1 R1 plus radius of gear 2, that is R2, is equals to the radius of gear 3, that is R3, plus the radius of gear 4, that is R4. That has been written here from the figure. R1 plus R2 is equals to R3 plus R4. You see the radius of gear 1 from here to here, R1, plus the radius of gear 2 from here to here, that is R2, is equals to the radius of gear 3 from here to here, and the radius of gear 4 from this point to the center of the output shaft. Therefore, it can be written as R1 plus R2 is equals to R3 plus R4. And we have assumed that module of the gears to be same. Therefore, when the module is same, the radius is directly proportional to the number of teeth on the gear. Therefore, R1 plus R2 is equals to R3 plus R4 can also be written as T1 plus T2 is equals to T3 plus T4. So this is about the reverted gear trains. Now we will enter into the important type of gear train, that is the epicyclic gear train. Now what is an epicyclic gear train? So as I told you about the applications, these are the applications and the advantages of the reverted gear train. Now when it comes to now we'll discuss about the epicyclic gear train. Now you see this combination that has been given here. There is a bar on which the gear A is mounted, and gear B is externally measured with gear A, and these gears A and B are connected with an arm C. Now, what is an epicyclic gear train actually? When one gear rotates upon and around the other gear, you call such a combination as epicyclic gear train. Now, you see this epicyclic gear train combination that is being shown in this figure can also be used in the it can also be used as a simple gear train. How you see this gears A and B are measured externally and which has been attached with an arm C. For example, if you fix the arm and if you rotate gear A in clockwise direction, then gear B will rotate in anti-clockwise direction because A and B are meshed externally. Therefore, such type of combination, you call it as a simple gear train. And instead of fixing the arm, if you fix gear A, then the arm and gear B will rotate upon and around gear A. Such combination, you call it as epicyclic gear train. Once again, if instead of fixing the arm, if gear A is fixed, the arm will rotate about the center of gear A and the gear B will rotate upon and around gear A. Such combination, you call it as epicyclic gear train. Now you see the another type of diagram of the epicyclic gear train. You can also call it as a planetary gear system that has been shown in this figure. So this figure shows you the planet gears which are mounted on the arms. Now you could see here the planet gears which are mounted on the arms. You could call it as a planet gear, or you can call it as a pinion gears also. This arm that carries the planet gears, you call it as a planetary carrier. And these planet gears are in mesh with the sun gear, which is at the center, which is mounted on the output shaft. You see the center gear is the sun gear. We call it as a output gear because the sun gear is normally mounted on the output shaft. This planet gears are meshed with sun gear and the annulus gear, or you could call it as a ring gear. Ring gear will have ring or annulus gear is having internal teeth. This is how the combination of the planetary gear looks like. And you can also see the animation. You see in this animation, the planetary gears are rotating in clockwise direction, and the arm which carries these planetary gears is connected to the input shaft. And you see when the planetary gears are rotating in the clockwise direction, automatically, because they are externally measured with the sun gear which is at the center and which is mounted on the output shaft. The center, that is the sun gear, will rotate in the anti-clockwise direction, which is mounted on the output shaft. Now you see what are the important elements of the epicyclic gear train. One is the sun gear, which is exactly at the central gear, or you could call it as a center gear or central gear. The second one is the planet carriers. They are small sized gears. And the third one is the annulus or ring gear, which has internal teething. Now, these are the advantages of the epicyclic gear train. The epicyclic gear train they are generally used to high uh, reduction ratios. They are having, very quieter operations, and they are very compact in nature and which will have high torque transmission also. And but the combination that we use, the planetary system, sun gear, the entire combination is very complex in nature. Therefore, that could be the one of the disadvantage of the planetary gears. And when it comes to the applications, these epicyclic gear trains or planetary gear trains are used in, you know, the automatic transmission of the cars, and these are also used in pulleys, wristwatches, milling, lathe machines, etc. Okay, so this is about the different types of gear trains. We have seen different types of gear trains and we have calculated gear ratio, speed ratio, and train value for the simple gear train. And we have also seen the speed ratio for compound gear train, and we have also calculated the speed ratio for the reverted gear train. And we have also seen four different types of gear trains, that is simple gear train, compound gear train, and the reverted gear train. Now let us see one simple example, numerical example of this epicyclic gear train. So an example is being shown here in the slide. So in an epicyclic gear train that is shown in the figure, you see an epicyclic gear train is shown with gear A and gear B, where gears A and B are measured externally and they have been connected with an arm C. So in an epicyclic gear train, an arm carries two gears A and B, which is having 36 and 45 teeth respectively. Therefore, given TA is equals to 36 and TB equals to 45, full stop. If the arm rotates at 150 if the arm rotates at 150 RPM in anti-clockwise direction about the center of gear A, that is, if the arm rotates at 150 RPM in anti-clockwise direction about the center of gear A, which is fixed, that is, gear A is fixed. In that condition, you have to determine the speed of gear B, full stop. In the second case, if the gear A, instead of being fixed, if gear A makes a 300 RPM in clockwise direction, what will be the speed of gear B? Now, in order to solve this type of problems, we use a tabular column method, which is being shown here. In the tabular, when it comes to the tabular column method, the first column we write the serial number, and the second column we write the condition that we are going to assume, and the third column represents the revolution of each element in the given gear train combination. Now the given gear train combination here, the epicyclic gear train has three elements, that is gear A, gear B, and arm C. So to write this table, first you have to write the table by fixing any one of these three elements. That means either you can fix A, you can write the revolutions, or you can calculate the number of revolutions for arm C and B, or you can fix gear B and you can write or calculate the number of revolutions of arm C and A, or you can fix arm, then you can easily calculate the number of revolutions of gear A and gear B. Now, when you have this type of combinations, generally fixing the arm is very easy to calculate the number of revolutions of the other two elements actually. That is what has been written in this table here. You see the first one, if you fix the arm, that has been written here, the condition of the motion, the arm is fixed. If I fix the arm and if I rotate the gear A for one revolution in anti-clockwise direction. You see, dear students, here, when gear A, if you rotate gear A in anti-clockwise direction, and if you take anti-clockwise rotations as positive sign, the all clockwise revolutions will be negative in sign. Therefore, because in this problem we have taken the anti-clockwise rotations as a positive sign, therefore the clockwise rotations, all the clockwise rotations will be in the negative sign. You see here that has been written here. The second part of the table, I mean the second column of the table consists of this is the first one. We assume that the arm to be fixed, the arm C is arm fixed, gear A. See, you can ask me whether I need only to rotate gear A. Can I rotate gear B instead of rotating gear A? Yes, you can do it also. You can, by fixing the arm C, you can rotate gear B also. By fixing the arm C, you can rotate gear A also. So here I am coming from gear A. Therefore, you see the revolutions table, in the revolutions of the elements table, whatever the element that has been fixed, that has to be written in the first column. And whatever the element that is being rotated first as an input, that has to come in the second column. And the third column will be the, the third element automatically. You see here, here in this figure, we have three elements, that is gear A, gear B, and arm C. Because we have fixed the arm C, the arm C comes in the first column. And by fixing the arm C, we are rotating gear A in anti-clockwise direction. Therefore, we can take this gear A as an input gear. Therefore, gear A comes in the second column. So because A is meshed with B, if I rotate gear A in anti-clockwise direction, gear B will rotate in clockwise direction. Therefore, gear B will come third. You see, because we have fixed the arm comes first, and we have rotated the gear A, therefore gear A comes second, then gear B comes third. Instead of rotating gear A by fixing arm C, if you rotate gear B first, gear B will comes in the second column, gear A will come in the third column, because in that case gear A will be output gear. In this case, because we have assumed gear A to be input gear and has to be rotated for +1 revolution in anti-clockwise direction, gear B will be the output gear. Therefore, gear B has been written in the third column. Now you see here, the first condition is arm fixed. Gear A is rotated for 1 revolution. +1 is given because it is anti-clockwise. 1 revolution anti-clockwise. Now, when it comes to the number of revolutions of the elements, as I told you, why I have written arm C here, then gear A and then gear B. For arm C, the number of revolutions are 0 because arm is fixed. Fixed means it doesn't rotate. Therefore, it is 0. Number of revolutions are 0. That is what we have assumed. And we assume that the gear A is rotating in anti-clockwise direction for 1 revolution. Therefore, the number of revolutions of gear A is +1. Now, if gear A is rotated in anti-clockwise direction for 1 complete revolution, what is the speed of gear B? What is the number of revolutions of gear B? Now, how do you calculate the number of revolutions of gear B? Simple, because we know the gear ratio formula, because gears A and B are meshed with each other externally, and gear A is the input gear and gear B is the output gear. So if we write the gear ratio, speed ratio between gears A and B, the speed ratio, that is, as you know, what is the speed ratio? Speed ratio is the ratio of driving gear to the driven gear. The driving gear is A here, the driven gear is B here. NA by NB is equals to TA by TB. NA by NB is equals to TA by TB. Now NA, that is the speed of gear A. Gear A is rotating in anti-clockwise direction. You put a positive sign in front of NA. And gear B is rotating in anti-clockwise direction. You put a negative sign. Therefore, plus NA by minus NB, minus because it is rotating in anti-clockwise direction, is equals to TB, because this is inversely proportional. Sorry, what I have told you is TA by TB. It is inversely proportional. TB by TA. TB by TA. Therefore, what is NA here? NA is 1 because we have assumed the gear A to be rotating for 1 revolution. You substitute 1 in place of A, NA. Therefore, NB is equals to minus 1 into TA by TB. That is how it comes for gear B, minus 1 into TA by TB. Minus NA into TA by TB. This NB is equals to minus NA into TA by TB, because NA is 1 here. Therefore, minus 1 into TA by TB. One has, we can remove it. Therefore, it is minus TA by TB. So instead of rotating for one revolution in anti-clockwise direction for gear A, if we rotate for x revolutions, what happens? That has been written in the second condition. You see the second condition, arm is fixed. The arm means here the arm C is fixed. Now instead of rotating for one revolutions, what happens if you rotate for x revolutions? Arm is fixed, therefore it is 0. In the first conditions, we have rotated gear A for one revolution, and therefore it is +1. Now here we are rotating it for x number of revolutions, therefore it is plus x. Now, what is the number of revolutions of gear B in the first case? It is -1 into TA by TB. 1 here because NA is equals to 1. Now, what is NA here? NA is x, therefore it is minus NA into TA by TB. NA is x because therefore you substitute minus x into TA by TB. Now, this is how the number of revolutions of gear B can be calculated. Now, in the third case, because we have assumed the arm C to be fixed. In the other case, you can fix gear A, arm C can be rotated also. Therefore, it is better to add revolutions for the arm also. Instead of that, we will do, if we add plus y revolutions for all the elements, nothing will happen mathematically. Therefore, adding plus y revolutions to all the elements. What are the elements here? Arm, gear A and gear B. If I add plus y to 0, it will be y. If I add plus y to x, it will be x plus y. If I add plus y to this minus x into TA by TB, it will be y minus x into TA by TB. That is the total motion. Total motions for arm C are plus y. Total motions for gear A are x plus y. Total motions for gear B are y plus minus, there is a minus, therefore it will be y minus x into TA by TB. You have to add the step number 2 with step number 3. 0 plus y is y, x plus y is y, minus x into TA by TB plus y is y minus x into TA by TB. This is how the condition of motion table can be written in the epicyclic gear train combination. Now you see, now what we have to find in this question is we have to find the speed of gear B when gear A is fixed. And you see here in this question, in an epicyclic gear train, the arm carries two gears A and B. Therefore, TA is equals to 36 and TB is equals to 45 respectively. If the arm rotates 150 RPM in anti-clockwise direction. Now you see in this conditions of the motion table, the arm C, what is the total motions of the arm? It is plus y. The total motions of the arm is plus y. And as it is given, the arm is rotating in 150, rotates at 150 RPM anti-clockwise. Anti-clockwise, all anti-clockwise rotations are taken as positive, therefore clockwise will be negative. Arm is rotated at 150 RPM anti-clockwise, therefore y, you see here that has been written here, since the speed of the arm is 150 RPM anti-clockwise, therefore from the fourth row of the table, y is equals to plus 150 because it is anti-clockwise. And you see the question, if the arm rotates at 150 RPM in anti-clockwise direction about the center of gear A, which is fixed, that means gear A is fixed. Now what is the total motions of the gear A? It is x plus y. Fixed means x plus y is equals to 0. That has been written here, x plus y is equals to 0. If x plus y is equals to 0, we know the value of y, that is 150. Therefore, x will be equals to minus y. Therefore, x is equals to minus 150. And we need to calculate the speed of gear B. What is the speed of gear B? The speed of gear B can be taken from the fourth row of the table. That is, total motions for gear B is y minus x into TA by TB. Therefore, you go to this and write speed of gear B, and NB is equals to y minus x into TA by TB. TA, TB are given. We have calculated the value. We know the value of y and we have calculated the value of x. If we substitute all the values, it will come around 270 RPM plus. Plus means clockwise. Therefore, it is 270 RPM. Sorry, plus means anti-clockwise. It is therefore 270 RPM anti-clockwise. Therefore, instead of putting plus in front of 270 RPM, we have written anti-clockwise in the brackets. What is the second condition in the problem? If the gear A, instead of being fixed, makes 300 RPM clockwise. See, in the first condition, the gear A is fixed, therefore x plus y is 0. So in the second condition, if the gear A is instead of being fixed, if it makes 300 RPM clockwise, clockwise means negative. Therefore, gear A, the total motions of gear A is x plus y. X plus y is 300 clockwise, therefore x plus y is equals to minus 300. And comes to the arm C, the total motions of the arm is y, and it has been given that the arm rotates at 150 RPM anti-clockwise. Therefore, you see here, since gear A, we have to calculate speed of gear B when gear A makes 300 RPM clockwise. Therefore, x plus y, the total motions of gear A, x plus y is minus 300. Therefore, x is equals to minus 300, y goes on the other side, minus y. So what is y? Y is 150. Therefore, that is equals to minus 300 minus 150, that is equals to minus 450 RPM. Now we need to calculate for this condition, that is x is equals to minus 450 and y is equals to plus 150. We need to calculate the speed of gear B, that is NB, that is it has been taken from the fourth row of the table. For gear B, NB is equals to y minus x into TA by TB. And we know the values of y here. What is y? The value of y, it is 150, and the value of x is minus 450. Minus into minus, it will be plus 450 into TA by TB, that is 36 by 45. The total speed of gear B, if gear A makes 300 RPM clockwise, will be equals to plus 510 RPM. Plus means anti-clockwise, therefore instead of putting plus here, anti-clockwise has been written in the brackets. So this is how we solve the problems of the epicyclic gear train by using the tabular column method. Thank you, students. Thank you for this lecture on gear trains. Thank you.